So, yeah, this is gameplay network programming, and as you saw, it's an open session. I've refrained from any particular specifics about games that I've been working on, so even if you're not from Sumo, you're welcome. And so my name's Wayne. I've been making games for almost 30 years now, which is a little numbing to say it loud, to be honest. Started my career as a junior engineer in Newcastle, and a team of just 5 programmers, which sounds fairly insane these days, but because of that team size, it meant I got a lot of experience in all parts of the code base, from gameplay and graphics, AI. I even wrote the scripting language, though at the time I had no clue what I was doing, so the less said about that, the better. When that project was finished, I looked back at the bugs that we encountered, and I thought to myself, there must be better ways of structuring code. And I was a junior, but I guess code issues are supposed to be expected on when you're a junior, but no one actually complained or anything. But just personally, I thought there had to be better ways to write code. So I bought a few books, I fell into the well of software engineering, and that's been my favorite subject ever since. If we jump forward about 10 years after that first game, I found myself working at a studio who was having problems finding a network engineer, and they asked if I'd fill that role because they thought my approach to programming might suit working within the network environment. And at the time I was a little dubious, and I told them I had no experience with network programming. They explained that they were well aware of that, but had confidence in me regardless. And well, the following week, I started working as the sole network engineer on that team, and the team would grow, but needless to say, I had an extreme crash dive into network programming. And that feels like a long time ago now. And the past few years, I've joined some projects that were already some way into development, and I've been brought on to help with their network implementation. So what I've found is that each project has made very similar mistakes in their approach to network gameplay, which brings us all to this presentation today. So what I'm going to try and do is cover those repeated mistakes and explain why they're mistakes, as well as what we can do to avoid them. And then the main goal being that as a group, we're able to skip past these common mistakes and end up with network gameplay that is in a good place later in development, which is where all the problems turn up. For this talk, I'm mostly going to be referencing Unreal Engine as a base. The reason for this is it's been around for years and it's well tested, and it's quite well known. But this is purely just to keep the talk fairly grounded on a technical level. What you'll find is that most network engines are generally quite similar, so they have the same features and functions. So even though I might be referring to Unreal, this talk should still be very relevant if you're using another engine. I'm mostly going to be focused on client-server-based games. It's still relevant for peer-to-peer, but client-server is generally the most popular format these days. And if you're using Unity along with the Mirror network library, I'll be pointing out some differences. In fact, the title I'm currently working on uses Unity with Mirror, so this should also be a relevant talk for you. As I mentioned, the feature set for gameplay networking is fairly common. Different libraries generally carry across similar concepts. So the features and approaches I mention here should be relevant, whatever engine you're using, even if it's neither of those two. It's just most engines have these functionalities. You may find some engines have different names for the technologies. So in Unreal, there's a technology called network relevancy, and in Mirror, it's called interest management. So this presentation doesn't mean you can skip the documentation for your library, but I will mention any significant divergences in naming of features. Let's come back. So one of the first things you might be wondering is where is your online team? And they are there, and they're usually super friendly and willing to help, but online these days doesn't necessarily mean they're going to be familiar with your gameplay networking library. They're usually well-versed in networking and communication, so even if they aren't familiar with the gameplay side of it, they're a great target for network-related questions. But in general, your online team is going to be far more focused on features requiring the network. This can vary from matchmaking to social features or friends, messaging, server lifetimes, these kind of things. So although they'd be well-versed in your network communication, they may not be specifically trained in your engine framework that you've decided to use for your project. And I have some good news for everyone. It really isn't that difficult. We just need to flick a switch in our brains which controls how we approach things. The switch is quite simple, but it's very fundamental, and it's different to how you would usually approach these problems in a single-player game. And it's the main problem I see people tripping up on when they start trying to do a network gameplay. So it means we have our first entry step is to require us to perform a little bit of mental gymnastics. But once we have, everything becomes simpler. And it's this stage that I think everyone falls over, not because they can't do it, but because they don't know that they need to do that. So in your standard single-player game, we'll normally approach problems procedurally. Now, okay, your code might be object-oriented in nature, but what the code is doing is essentially procedural. We do this or we do that. And unfortunately, in network world, this becomes a nightmare mass of spaghetti. This is mostly caused by the time it takes for information to travel across the network, coupled with the lack of guarantees in which order they're going to arrive. This leaves your code uncertain in the world in which it exists. And as developers, we try and address those problems, and we add more code, and we end up with all this spaghetti. So we need our code to be resilient to both order and time, which sounds like an episode of Doctor Who now, I say it out loud, but the internet is a really unfriendly place, and data needs to travel through it, so procedural just isn't the way. We need to switch away from that and in our brains, and our code can still be object-oriented, but we need to move away from procedural and become state-based. And it's this fundamental approach that will transform your network gameplay from a spaghetti ball into something entirely more awesome. Now, before I go any further, we need to stress this up front because I think it's so important. In your network journey, you're quickly going to come across something called remote procedure calls, or RPCs for short. And every library has these, and they allow you to declare functions that you can call, and they will run over the network. They will seem magical, they'll seem awesome, they'll seem super simple to understand. You can call a RPC function on this machine, and it'll execute over here on this machine as if by magic. They'll look like a perfect solution to many problems that you're going to come across. They'll look super simple to use. They'll just seem amazing, and everyone seems to jump on remote procedure calls. And you'll be tempted to dismiss this talk because RPCs allow you to carry on in a procedural way. But they are not. They're the number one source of network-related issues that I encounter by far. I'm going to come back to RPCs towards the end of this talk, but I really want to stress this point up front because they're a really bad choice for a significant majority of the network code that you'll need to write. And I've encountered all kinds of reasons for RPCs, and they've all been wrong reasons to use an RPC. So we need to try to solve your game-related problems with a state-based approach. And I promise you, RPCs will look like the easiest solution, but they're not. They'll lead to buggy code. They'll lead to spaghetti, where your code doesn't even know what the hell is going on anymore, and you'll try and patch your code, and it will get even worse. If there's nothing else of interest in this talk, I want you to walk away with an inherent distaste for RPCs. And I'm only bringing this up now in the beginning because everyone jumps onto RPCs, and I've seen them used all over the place, and they just make everything fall over. So yeah, we do not like RPCs. So what is this magical state-based programming that I speak of? We need to take a brief look at the concept, which, as I said, is actually quite simple, but it's a slight mental somersault because it's different to the way we normally write things. And so each object in our game has some kind of state associated with it, and what that state consists of, it's entirely up to you as the developer, and this is pretty much object-oriented programming, so it's not a radical change from what you're doing. The main part of data-driven programming is that the state is self-contained and that your object relies entirely on its own state to perform any of its behavior, which means we don't ask other network objects for information we're interested in, which may be communicated over the network. If we do this, there's numerous network-related problems that we'll come across that means we might not have the information we're expecting to have, which is where our problems come from. And we also need our objects to be able to switch from any valid state to any other valid state. And this switch should be possible instantly and handled correctly. So for example, if we have a character who's been knocked to the floor and they need to be able to get up and open a door, we should be able to jump from lying on the floor to opening a door without the intermediary step, if our state tells us to do that. When an object state is modified, the server will gather all of the values that have changed on that object and send them to the client all together. And this means if you change several values in a frame on the server, you won't get partial updates on the client that is only a few of those changes. You'll get either all of those changes or you won't get any of them. But there's no guarantees that any other object in the game world has received an update just because your object has. Okay, another example. Let's say we have a character who wants to open a door. The character has an open animation where they reach out, grab the door, and push it open. And the main network issue with that behavior is that the door's open animation must be synchronized with the character's animation. And there are several approaches you can take for that issue. One is to have an intermediary object whose state is replicated and whose job is to control the animation on both the character and the door. Or we could have the door control the animation of the character, or vice versa, depending on how we structured our code. The point here isn't which approach we use to control these animations, only that we've considered how to control these two things with one object state, whether that be the character, the door, or an entirely new object whose sole goal in life is to manage the synchronization of those two objects. The point is state, a single state that is self-contained. And when writing our objects, we need to keep in mind that we do not know the state of any object beyond ourselves. And if there is data in another object that we need, it should be part of our state. Oh, whoops. I knew this was going to be a problem. So we manage and respond to state changes via notifications that we receive from our network library. In Unreal, we specify the function to be called with when a property changes using a uProperty declaration. As you can see up there. And in Unity Mirror, we use a C# attribute that specifies the hook function, and we can see that they're almost identical if we take into account that these are completely different languages. And we need to remember also that these functions up here, the replicated using, they're not automatically called on the server. This allows you to make several property changes on the server before calling the handler, whereas on the client, you're going to receive all the changes before that method is invoked. So execution-wise, the body of this method should be the same on the server as well as the client. So, just checking. Yeah, so I have a simplified door example here to help clarify a little. We have a Boolean saying whether the door is open, and when the value changes, the onRep function is called. Inside this handler function, we simply check whether or not the door is open and call a configure function. This function would either show the door open or closed. And I put it in a function here just to make the pseudocode a little bit shorter. It could be inlined or you could put it in functions like that. Now, if we want to make this more complicated, say, for example, we want the door to animate open or closed, we can just build on this example and replace the Boolean value with a scalar that allows us to control the animation. What I would recommend is that you build the basic state you want to begin with and then expand that state over time. Approaching behavior like this in a state-based way leads to code that can be easily refactored just based on, because it's just controlled from your local state. Now, I added this example a bit late, so this is not the best example, but if we consider a live leaderboard displayed in game, this leaderboard displays the ranking of the local player, along with players on either side of them in the rank listing. What we can't do here on the client machine is look at all the players we know about and build that list locally, because the problem with this is that we don't know on our client machine if we even know about where all these players are. And the players that we do know about, we don't know if we have the latest information about those players. So such a leaderboard is not entirely possible just by looking at the state of the world on the local machine. If we need to do something like this, we would actually need to create a whole new object whose role in life is dedicated to managing this displayed leaderboard. And we would just we would replicate it from the server specifically to the client. So most engines have some kind of player information object that we can use, and if not, we can create our own object, and we can set the relevant owner to true, setting the desired client as the owner, and we would have to create multiple of these for all of your clients. We then have all ways to control how frequently we talk to the client, to control the bandwidth usage, such as sync interval, which we'll come back to later on. So, and with this example, something I don't want you to take away is that your UI should go through the network. In fact, most UI should be entirely based on the information available on your client. For example, if you have a mini-map or some targeting reticle system, these should all be entirely client-side driven because they're representing what the player is seeing. The difference with this particular example is that the list could contain any network objects in the game, and as a client, we don't know if we have the latest information for all those objects. It's just an example I came across recently where a client machine was expecting to know all the information about all the objects, and I thought it would be useful to add in here. So the main point of this slide is just you can expect to know about all of the latest information of all the objects on the client, because there's various reasons that the server will not tell you the latest information, so you have no guarantee. And here we would have to create a whole object whose entire lifetime is there to ensure that you have at least the subset of information that your client is expecting to have. So when we're declaring our state properties for an object, we should avoid unbounded arrays at all times. The main problem with unbounded arrays is that, well, they're unbounded. Even if you know what the data limit is for you, if it's unbounded, it's open to someone later in development coming along and just sending megabytes of data over the network and not realizing it. I also consider strings unbounded. Most of the time in my experience, strings take the form of error messages. Instead, have some kind of string table and send an integer, which can be used to look up the appropriate string. If you must send an array, prefer an array with a fixed capacity. In this way, at least we're consistent in the bandwidth that we're sending, but we should try and avoid arrays when possible. And if we do need to use an array, use a fixed array, not an unbounded one. So, I mean, that's the basics of state-based programming, and in hindsight, I could probably do a whole presentation just on that alone. But there's a lot more that I'd like to cover, so I'm going to move on to replication. At a high level, replication is the name given to the process where the server sends object state from one machine to another. So each game tick, the server will run through the active network objects for each connected client. It will also look to see if the object is relevant for the client, and if it is, whether the object state has changed. So once it's done that, it will go through the selected objects and start to build a packet of data to send to the client. And this packet has an upper limit, which if we exceed it, the engine will start discarding objects based on their priority for the client. And we'll come back to priority as well. So once this packet of information has been built, it simply fires it across the network to the client. Now, all frameworks are going to have this kind of replication phase, and they're all going to behave like that with only slight differences. So understanding at high level what is going on during replication is super useful, and it gives us context for the content of the next few slides and allows us to make some more informed choices, more informed decisions of the choices available. So we know that the replication phase is processed by the server every frame. However, we don't really want all objects to replicate every frame, and we can control that using the network frequency property. In Unreal, this is called net update frequency, and in Mirror, it's called sync interval. The main difference between these two implementations is that in Unreal, you specify how many frames a second an object should replicate, which defaults to 100. And in Mirror, it's a time interval between replication, which defaults to 1/10 of a second. And because replication happens on the server once per frame, it's worth bearing in mind we can't replicate faster than our frame rate. So if you have a 30 frame per second game in Unreal and it's using the default net frequency of 100, it's still only going to replicate 30 times a second because that's our frame rate. If we've written our objects in a data-driven way, they can be surprisingly resilient to different frequencies, and when trying to optimize bandwidth, it's worth looking at that value just to get some really easy savings. And just to reiterate, RPCs completely ignore net frequency, so we cannot use that to control the bandwidth caused by RPC calls. I might need some water. So on the client side, we'll receive the replicated state from the server, and the properties of our objects will be updated, and the client will then invoke the notifications associated with the properties that have changed if we've specified one in our replication. So whilst we can trust that our object state has been updated and we can use the associated value in our handler methods, we need to keep in mind that we are not guaranteed that any other object has been updated. It could be that the other object is discarded due to size. It could be considered irrelevant to the client. It could be that the frequency was lower. It could even be that the local machine just hasn't processed it yet. And the point being, there are many reasons we don't know why. We don't know if any other object state represents the latest state for that object. And we may never, if the server considers an object irrelevant to our client, we may never receive that information. So this is a major issue when not using state-based programming, because then we have to worry about when do we get the state or where is this state. And many people come across this issue and they attempt to solve it with remote procedure calls. Do not do this. So network frameworks typically allow us to replicate object pointers or references over the network. And to do this, each object has a network identifier assigned to it, and your engine will convert the reference to the network identifier, send that over the network, and look up the object on the local machine. Voila. Pointers replicated over the network. And if we go back to our door example again, this allows our character to be able to reference the door they're opening. But as I just explained in the previous slide, we cannot guarantee the referenced object has had its state replicated. So this can be quite a gotcha moment. It can be during development, everything works great, but as soon as you go live or let down the development cycle, things start to fall apart. As much as it's really useful to pass these object references around, we need to use them with extreme caution. If the state we're interested in is replicated, then we can't trust our local copy. For example, it's unlikely our door location is going to change during the lifetime unless you have flying doors in your game. If our object is static, we can safely just grab the location of the object from the reference. But if we do have an object that moves around and we want to access a replicated property on another object, we're a little bit stuck. So what we need to do is add a copy of our dependent data to our original object, update those values on the server, and have those replicated to the client as part of our own state. And this ensures we have the latest data along with our latest state without the dependency on another. So in this particular example, if you, let's say you want to have a character stand in front of the door, rather than trying to get the position of the door from the door itself, well, we'll assume the door can move here. What we would do instead, your character would have door location as one of its properties. And on the server, you would just copy the door location into that property, and that would get replicated to the client. And then on the client, you would know that your local property of door location is the same as when it was accessed on the server. So yes, I wanted to mention RPCs once again, and I am trying to convince you of this fact. RPCs inherit all of the issues I've mentioned with regard to replication, but they came with their own additional problems to go with it. If you ignore any of my warnings, things will seem fine and everything will seem great. But over time, you'll encounter nightmare issues that are extremely difficult to resolve because they become so ingrained into your code base. So remote procedure calls bypass the replication framework. They negate everything mentioned in all preceding slides and also in the next few slides. And I will come back to RPCs a third time, but I hope I'm building enough of a case for you to just say no. So that's like a bit of a crash course in replication, and there are some things we can use to control how objects replicate over the network. So the next thing I'd like to introduce you to is network dormancy, and unfortunately, Mirror doesn't actually have this currently, so this is going to be quite an Unreal specific section, but I'm hoping in my current project I'm going to be looking at adding some form of network dormancy to Mirror if we get the time, which is going to be up to Dal. So as described previously, during replication, the server will inspect every object, every frame for every client, and see if it needs replicating. If we have a level with, say, 1,000 doors, which effectively do nothing until someone interacts with one, we can lose a whole bunch of CPU cycles inside the replication phase due to so many objects that are doing nothing, essentially. So instead, what we can do is make our object dormant on the network, and doing so effectively removes the object completely from the replication phase, and we can recover all of that CPU time back. And this is fantastic for objects that are not awake all the time. Doors or platforms that rest in one spot and then move, just about anything that doesn't really need constant replication. In a typical game, it may be that the player characters themselves are the only live network objects all the time, and other objects such as dropped keys or doors are generally alive for only a short period of time before they go to sleep, which means there's a lot of CPU cycles we can save with the use of dormancy. And to take advantage of network dormancy, we just need to set the net dormancy property to dorm initial in our constructor. And this tells Unreal that the object is dormant and in its initial state. And as long as this initial value remains, it allows Unreal to know that the object has not changed from its initial state. When we do change our object and have it replicated, which we'll get to in the next slide, the net dormancy property is set to dormant or, which tells Unreal the object is dormant, but it's not in its initial state. And this allows Unreal to make choices on what to do when a new client enters our game. And of course, we do want our objects to replicate sometimes. In Unreal, when we modify the state of our dormant actor and we wish for that new state to be replicated, we can call flush net dormancy, and this will effectively wake the object up for the next replication phase, causing it to replicate before sending it back to sleep again. If our net dormancy is currently set to dorm initial, Unreal will automatically change it to dormant all for us, and this puts our object back to sleep until we call flush net dormancy once again. This is great for network objects. We can even call flush net dormancy from within blueprints, should it be needed, allowing dormant objects to be easily extended. However, it does require people to understand dormancy when extending objects in this way. So I would normally try to wrap all the dormancy control inside C++ code. Failing that, hopefully the person managing the blueprints is aware of dormancy and how to use it. So this is great for objects whose state changes instantly but very infrequently. Our original door with the Boolean, for example. But there are other objects that dormancy is great for too. These types of objects may be dormant for a time, then wake up for a short duration before going back to sleep again. And one way we can handle these is to just call flush net dormancy every tick, which works, but it's not the best approach. And rather than that, Unreal provides us with an alternative. So besides flush net dormancy, we have another method that allows us to change the dormancy of our object, and that method is called set net dormancy. And if we consider a platform that moves from one location to another, then goes to sleep for a time before it wakes up, and it moves back. In this case, we can set the object as dormant like before, and when we want the object to wake up, we call set net dormancy with the dorm awake value. And what that does is essentially flip the object into a live state on the network, and it will now replicate just like any other object, as though dormancy wasn't even a thing anymore. And for our floating platform, it begins life as dormant, then the server decides it's time for it to move, and we call set net dormancy with the awake value. The platform then moves along its assigned path until it reaches the end. At this point, we call set net dormancy once again with the dormant all value, allowing it to go back to sleep. And with this basic API for managing network dormancy, it becomes super easy to manage a lot of network objects in a game with little CPU time consumed on the server. Dormancy is an essential feature in Unreal Engine, I think, to manage all the objects in the game and to make sure that they're not all constantly alive and being processed by the replication phase. And I'm not sure if that sounds complicated or not, but it really is quite simple to use, and it's super efficient. So take advantage of that whenever you can. And as I said, I love dormancy as a feature, and I'm hoping I get some time to implement something with Mirror that mimics this behavior, because it's really, really useful. All right, so for all those who are using Unity and Mirror, you can come back from resting your eyes, and because network relevancy is relevant to you too. If you can remember all the way back to the beginning, you may remember that I mentioned network relevancy is the Unreal name of this feature, but in Mirror it's called interest management. So if we have a character moving through our world, it doesn't really make sense to replicate an object that's miles away from where our character is standing. They're never going to interact with it or even see it. So essentially the object is irrelevant or not of interest to a particular client. So if we were writing a graphics engine, we might say that the object was cold. Saying that, I should point out that relevancy doesn't affect the rendering of the object. So if the object was not relevant, it may still be seen on the client if you do draw it. It just won't be receiving network updates. In Unreal, by default, relevancy is simply decided based on its distance from the client. And there's a property on the object called net cold distance, which determines how far away an object can be before it's cold. If you're using Mirror, there are several interest management components provided with the library, and you can specify which one you want to use on the network manager instance in your game. You can also create your own interest management components if you wish, with a more fine-grained management specific to your title. I would look at the documentation because it's got like 8. I was going to list them here, but there's just too many for me to go through in here. Oops, come back. And as Unreal, hang on. Yeah, so as our server builds the data packet to send to the client, I briefly mentioned that it begins to throw away object data if the packet gets too large. The size of this upper limit shouldn't be a problem, because if your network game is handling this correctly, it doesn't matter that these are being discarded. That's just how the network is processing everything. If you're using RPCs, that becomes way more difficult. And the objects it discards is based on a property called network priority, and this is a floating point value you can assign to each object. The priority is used in a load balancing technique, which multiplies the priority with the time since it last replicated, meaning even if an object is discarded, it will get replicated eventually. It will just be at a lower frequency. The higher the priority of an object, the more bandwidth the object is given in relation to other objects. So an actor with a priority of 2 will be replicated exactly twice as frequently as an actor with a priority of 1. And this is super useful to ensure some objects get replicated more frequently. Perhaps there's a missile in your game that you think is really important for the player. But this is something that you can play with because it's all very game specific. And I don't think there's a priority in Mirror, but so I think this is specific to Unreal as well. Okay, so if I've done my job correctly, you should be recoiling in horror at this slide. I don't hear any hissing, so I maybe need to push harder next time. Remote procedure calls allow us to declare a function and specify whether it should be executed on the client or the server. And we can call the RPC, and it'll be invoked on the desired machine or machines. Now, I can see everyone's fears wanting at this point. It kind of sounds cool, doesn't it? So the problem with RPCs is that they're asynchronous and they're transient. So meaning once you've called them, they are forgotten. If a new machine connects to your game, they'll never get any prior RPC calls, nor any state you might change within the RPC handler. Some games have mentioned that they do not support new players connecting to a game, which is certainly a choice design can make. But what about disconnected players? Are you saying no, none of those can ever reconnect to your game again? If you are saying that, are you willing to bet that decision will never change for your development lifetime? If you ask design that question, do you think what do you think they'll say? So even if your game does not support new players joining, I would submit that your game is not really networked if that is a technical impossibility. On top of that, our RPCs completely ignore the vast majority of engine features available for us when controlling our network communications. It ignores frequency, it ignores dormancy, it ignores relevancy. You lose so much when you choose to use an RPC. Another common use for RPCs that I've come across are object actions, which stem from standard object-oriented practices. So if we have a door that we can open, sure, we can provide an open operation on the door object, make it an RPC, and it means we can open doors over the network in an object-oriented way, which sounds amazing. And logically, I would agree with that, but there are some problems that should make us pause. The act of opening a door is a character interaction, and it really should go through your input system. And this way, the server will find the appropriate door for you and validate the action before it executes it. So if we have the function embedded in the door itself, we bypass all of that, and we need to write some bespoke validation right inside the door itself. Now your door has to worry about a lot of external things. It gets messy. It also means a hacker only needs to find your open RPC on the network, and they can call it on any door that they like. And if the action has to go through the input system, at least the request must be validated. The client can also just call the RPC on any door they like. So I'd recommend you don't use RPCs to do such actions, but rather go through the input system, because that's exactly what the input system is there for. Oh, I keep missing the end one. Another common reason people give for using RPCs is that someone has a state change, but they found that using an RPC, the state change gets to the client faster than state replication. We've already seen that there are many ways we can control how state is replicated. We do not have that kind of control with an RPC. And state and RPCs both go over the same network, so there's no real reason that any one is any faster than the other. We can change the sync interval to send updates faster over the network, but that only makes sense if we have a high priority object, and it's a global change to how frequently the state is replicated. An alternative for objects with much lower frequencies is to use the network dormancy and use flush net dormancy on all the awake state. And this retains all our control over the framework, provides this retains all the control our framework provides over the replication frequency. And finally, there's also a function called force net update, which forces the replication system to replicate that object, that frame, regardless of any frequency setting. Now, that function's a bit of a sledgehammer, and I'd recommend avoiding it as much as possible, but sometimes you do need a sledgehammer. So I'm giving RPC calls a really, really hard time here, and such a hard time that I'm sure you're beginning to wonder, if RPCs are so horrible, then what is the point of them existing in the first place? So I may give you whiplash here because I'm about to do a hard 180. RPCs are really cool when used appropriately. My distaste isn't actually RPCs themselves. It's just the biggest common issue with networking that I've come across on multiple projects, not just one project, this is multiple projects, is the use of RPCs in general gameplay. And they've been used for state, they've been used for actions, they've been used for UI. And part of the problem is that they're just super simple to understand and use. So people grab onto them immediately and start doing this. And then the RPCs become ingrained in your code. And then you start getting issues and you start building code around those issues to try and fix those issues. And it just gets more and more complicated. And in the end, no one knows what the hell is going on anymore. So RPCs are great for transient data that doesn't impact the current game. If we think of data collection, they're great for page data, like in-game stores, if you have pages of items that you can click through, or database queries that have no direct impact on the game itself. They're useful for social actions, such as adding and removing friends. Basically, as long as it has no impact on the game world, then RPCs are really useful. But this is a very small subset of the game networking that you need to be writing. And it's not a silver bullet for everything. Oops. So I really hope people have been enjoying SDC, and there's been loads of great presentations from all the Sumo studios. There have been a few more network-related presentations if you'd like to delve even deeper. Dennis has a presentation on physics simulation replication, which talks about replication. Well, we talked about replication at a high level today, and his talk, for anyone who wants a lower level insight into that. And Mark had a great presentation about determinism over the network, which has loads of low-level information too. They've both been presented now, but if you missed them, I would look for them online when they're made available. So what I tried to do in this presentation is get the most useful information I could as fast as possible. There's been so many issues with a lot of the games that I've joined later in development, and it's too late to fix all of those issues. And those issues are mostly being caused by RPCs. And as I don't hate RPCs, but if you use them inside your gameplay system, you are going to come across a lot of problems later on, even if it seems to work at the beginning. And as much as I try to rush through that, I hope it's been of some use. Yes. Yeah, we can take questions, I think, if we have time. The end came up a lot quicker than I remember it. So.
Hello, thank you for the talk. That was really interesting. So you mentioned, I'm mainly a Unity developer, so you mentioned kind of Mirror for Unity. Have you looked at all of their new networking package as well? Have you got any impressions of that?
Haven't you? So I mostly worked in Unreal, which is why I picked that. So I'm currently working on a Unity game right now, which is using Mirror. They chose that before I came on that project, and I'm going to guess they've done their due diligence and they know that that's a good library. So
I think it was only released, I don't think they only had a stable release fairly recently, so it's probably only stably released after they started, I imagine.
Yeah.
Hi, so great talk. Thank you for that. And I have a question regarding the managing the dormancy or relevancy in Unreal.
Yeah.
Because my intuition is that the best way would be to use significance manager based on either location or the perspective, because it's easier to manage other stuff too at the same time. But what would be your recommendation to properly manage dormancy and or relevancy in objects?
Relevancy can be, it's quite title specific. It's hard to do a general solution for relevancy. It's a variable there that you can kind of apply your knowledge base for the game that you're working on. Well, the default implementation is just based on distance. There is a function you can override that allows you to put in your own logic into the relevancy calculation. But it's hard to say without knowing a specific game type.
Distance is enough.
So if you combine relevancy with priority, if you have relevancy where its distance will control what is relevant to you, but then priority you can use priority to make sure that closer objects get replicated more frequently. So it's kind of a combination of those two things rather than, it's better to keep relevancy as simple as possible. I mean, if you've got different rooms, you can always have connections in the rooms and just base which rooms can you see from where you are. But again, that's a very title specific solution. So, but yes, a combination of relevancy and priority I would use. I am planning to go upstairs to the code table after as well, if there's people who don't want to ask questions on the microphone.
Hey, yeah, thank you very much for the talk. It was very helpful. Would you consider remote procedure calls for sending the controls inputs from client to server?
Is this with Unity or Mirror? Sorry, is this with Unity or Unreal? Sorry.
Doesn't really matter.
So I would usually use your input system. Mirror implements your input system using commands rather than RPCs, and commands are just a fancy of a name for RPCs, but they're dedicated to that kind of, it's kind of semantically different rather than.
But the concept is the same, basically.
Yeah, I would try and go through your input system, whatever input system you have in your game. There could be various different implementations of input systems, but for interactions, I would try to go through your input system, because then on the server end, you can process your input system, and if you add new actions, it's easy to just add them to your input system, whereas if it's like a big web of actions that you can call, it gets complicated.
Thank you.
Dane here.
I heard you mention books at the start, and I like reading books, so I was wondering if there were any books you'd recommend on the subject of real-time network programming.
So I would, not so much on real-time network programming. What I used to do was read a lot of the blog posts by John Carmack and Tim Sweeney, and Tim Sweeney's got loads of stuff on Unreal's network implementation, and there's some really cool stuff from those.
John Carmack and Tim Sweeney.
Pardon?
John Carmack and Tim Sweeney.
Well, yeah, that's, as far as network programming goes, they're kind of top tier.
Cool.
Even if they don't do it anymore, but they've got lots of posts from the past. And the network implementations, they haven't changed that much. They're still basically what John Carmack and Tim Sweeney did.
Hello. So I think one of the things that Mark said in his talk from with Floats was that networking is everyone's concern, more or less. It stretches across the entire project. And one of the things that we found in some of our games is especially with Blueprint, designers go nuts, and what's their first thing that they reach for? It's the RPC. So what kind of things have you done in projects to kind of try and rein in designers, or is it just a case of educating them the same as a gameplay programmer? What kind of things have you done?
It is, you need to keep an eye. So my problem is I've always, especially the past, I would say, 7 years, I've mostly jumped onto projects that are already like a year and a half into development, and they've already got to a point where they have problems, which is why I've come onto the team. Yes, you need to keep an eye on the RPCs that I would probably try and restrain design from actually adding those in, especially because blueprints can become a nightmare to track down what the hell is going on. And it becomes more difficult if you introduce dormancy as well, because then design has to understand dormancy. On one of the projects I was on, there was a guy that I worked with that was really good. He was like working with the blueprints, but he was really good when I explained to him dormancy, and that went much better once I worked there. But I would get them to, I wouldn't get them to use dormancy, but I would at least try to teach them some dormancy practices if that's what you're using. But yes, you need to keep an eye on what design is adding network-wise.
Yes, may I have our last question?
Just on the point about blueprints and working with design on that, it's well worth catching Michelle Chapman's talk from this morning, the technical designer talk, because she lays out kind of like different stages of blueprints. There's kind of an intent blueprint, prototyping, production. And if you work with designers and tech designers on that, then what you can do is you can have stage gating where when you're moving from prototyping into production, you get code, you get network involved at that stage, so that you can pick up and review the blueprints and pick up network potential problems before they get turned into production.
Hello.
Oh yeah.
So on network relevancy, they've implemented now the replication graph, which kind of overrides the network its relevant for call. If you've overridden that a lot in your program and then you try to move away to use a replication graph, do you have any advice for how to handle that? Because I've seen a lot of things break that you've overridden your net relevance for, and now it's going back to the
So what have they changed to?
standard approach.
What did they change to affect the replication?
It kind of packs everything up into areas, into a spatial 2D grid of it, and it's more of a cheaper way to replicate it's cheaper on the CPU than packing up what running is net relevancy for.
So that should still be cool, as long as it doesn't slice up the objects, which is why the state-based stuff is really important, because if something started slicing up objects and their data, that would be a huge problem. If it's just separating out the different objects and what should be replicated or not. If you're state-based, I won't say it should just work, but it should be more stable, shall we say.
Okay.
So once you implement stuff in a state-based way, it's surprising how robust everything becomes.
That might be all the time I have questions.
That's all the time, okay. But I will be going upstairs if anyone wants to chat informally rather than here.